Well, if there are no other things, hi, hello. Welcome to section number 3. So lecture 3 was a little bit different from like the bulk of lectures 1 and 2. Lecture 3 has to do with stereochemistry. This kind of like how do we think and talk about the 3D structure of molecules. And that's going to be like a new skill for most people in the class. And also it's one that's kind of difficult and requires a fair amount of practice and visualizing things. So I've divided up kind of some of the big skills that we have to do today into 5 main areas. This extra challenge problem thing is a typo from when I teach in the summer. So first off, we're going to start with assigning E and Z and R and S because that's a little bit more regimented of like a lot of strict rules. Then we'll talk about kind of all the like definitions and vocab that we have with different stereoisomers. And then we'll go into this section that's called discerning stereoisomers. And I'll talk more about it then, but we don't have any actual section problems on it, but I think it's the hardest thing from this lecture. So we'll talk a little bit about that. And then we'll end off with chair conformers. So that's our game plan. If you could just take a second and scan the QR code for today. I forgot what the fun question is. I've liked reading y'all's responses, those of you who have been responding. And also for the video people who are joining us through cyberspace later, feel free to like fill out the QR code. Let me know who you are if you are watching this. From grading some of your problem sets, I know some of y'all are watching the video because I saw you do little things that I do in my section. I said, I see you. I see you. I had to grade question 3 for the problem set, and I hated that it was a bit nitpicky with some of the orbitals, like the drawing of the orbitals. So I would definitely encourage y'all to like take a look at the key for it. The biggest thing was like issues with shading and like the size of different lobes and everything. But without further ado, let's jump in to E and Z configuration. So for simple alkenes, we have this system of labeling alkenes as either cis or trans. And cis or trans system works fine if you have hydrogens on either side of the double bond. And so if the hydrogens are on the same side, we say it's cis. If they're on opposite sides, we say it's trans. This is about as deep as like biologists get into like chemistry structure with double bonds. But what happens when we don't have hydrogens, when we have complicated things on each of the ends? Well, we need a different system to kind of specifically indicate one version versus the other, because we can always like flip 2 of the things on one of the sides. Like, for example, with this molecule, I want to be able to distinguish this from the version that has the isopropyl here and has the OH down here. So we developed these terms E and Z. And what we are going to do, the whole process is we take a double bond and we are going to split it perpendicularly. So we are going to divide it into a left half and a right half. And then between the left and right half, we are going to use these ranking priority rules to determine who is the highest priority. And so we'll talk through those in a second. But if your highest priority things are on the same side, we say it's a Z alkene. And the way to remember that is that they are on the same side. Ooh la la, the same side. It's cheesy, but it works. And then if the highest priority things are on opposite sides, it is E, or they're on opposite sides. And that's my teaching all organic chemistry from Georgia. You know, my roots, opposite. Yeah, they're really from Zusammen and Entgegen, like German terms, but like I feel like Zusammensein and opposite are a little bit more fun. But let's talk about these rules. So I really think about these rules. They're called the Kahn-Ingold-Prelog rules, which you'll never have to like regurgitate that name, but just in case you ever see it. I really view it like the card game War, where you like flip over cards and then like you see who wins. And so these are the rules for who wins in kind of an atomic scale. So the first rule is atomic number. The highest atomic number wins. So maybe let's look down here at this alkene in the first practice here. Also, by the way, for this practice, these are just ones that I have made for some simple kind of quick practice. These are not on the actual section problems document, so just heads up on that. So if we take this alkene and we split it perpendicularly into left and right side, if we look at the right side, on the top we have an oxygen, on the bottom we have a carbon. And so if we go with the rule that the bigger atomic number wins, we already have a winner. So this oxygen up top wins. And one thing I really like to do, just to keep myself straight with this, because it's really easy to make a careless error, is I like to put a star for the top or bottom side where we have a winner. Just because if you figure out the winner but you don't notate it somehow, then you might like forget that when you go to do the other side. So that's rule number 1. Rule number 2 is isotope. And this one, I think it was kind of elided in lecture, or it was kind of like a sub-bullet, mostly just because you don't see it that often. You might see it a little bit on the practice problems or homework, so I just throw it in here just to see. But if you are tied here for the type of element, like both of these are oxygens, but one of them is normal oxygen 16, and one of them is the heavier isotope oxygen 18, then the heavier isotope is the one that wins. So here oxygen 18 wins over 16, and if there's an isotope, they have to explicitly like say that. So if you had like carbon versus carbon 14, they would have to put the 14 in there to tell you. But again, kind of rare. And then the last thing is substituents. So the atom with the highest atomic number substituents wins. So let's look at this. This is, if we look at the right side here, we have a carbon versus a carbon. And what we're going to do is we're going to list out the 3 things it's attached to as we go out from the double bond. So everything behind the carbon in question, think of as scorched earth. We are not going to touch that. We want to know what things are attached to this carbon as it branches outward. Well, this carbon has 2 implied hydrogens here, and it has a bond to this carbon. So the way we've write out the substituents here is CHH. The bottom one, it's going to be the same thing, CHH. There are 2 hydrogens on here, and then it's attached to a carbon. Again, we never really want to go back for the most part. Then we see these are tied, CHH, CHH. And so if we tie, we go one step out and do the same exact thing. So now we are comparing this carbon and this carbon. The top one, remember we have a hidden hydrogen in here, same down here, that's implied. The top one, we only consider the things that are going outward from the double bond. So it's connected to a Br, a carbon, and an H. The bottom one down here is connected to a chlorine, a carbon, and an H. So if we have to figure out who the winner is, we go with whatever has the highest atomic number substituents, and bromine is going to be higher than chlorine. The CH is kind of tie. But really, you just need whoever has the highest between both batches. So our highest priority is going to be over here. Now we see our stars. We have our highest priority on the bottom on one and the top of the other. And so, are they on the same side or are they on opposite sides? Well, they're on opposite sides. So we would say that this is an E alkene here. So that's kind of our process. And we're going to do some practice here to go over these rules and see it in a few other settings. Now, normally, like in teaching, this is where I like give y'all a few minutes to work on your own, and then like we come and check it. And I want to do just like a little poll of like the 5 of you who are here. Like, do you want like a couple minutes to work on your own and then we come back and check? Or do you want to just do it together? Because the other side of it is like for the video and things, people can always like pause. But yeah, so please write in the chat. Do you want time to work on your own or do it together? Okay. We have 2 votes for together. Oh, Fallon. Okay, we have 2 versus 1. Anyone else want to come and tie this up? Oh, okay. I think the togethers have it. 3 out of the 5 right now. So sorry. Feel free to like mute me and like you could like watch the video back later if you want. But let's do it. So we've already split this double bond. We've already done the right side. It was just atomic number. For the left side, we are going to compare this carbon and this carbon. They're both the same atom. So we look at substituents. The top one, well, we look at what is going away from the double bond. We certainly have 2 carbons here. What else do we have? Hint, it's the hidden thing that we always have to make carbon have 4 bonds, unless we have a formal charge. It is indeed a hydrogen. Very nice, thank y'all. Cool. So the top one, we would say its substituents are CCH. And the bottom one, it has 2 hidden hydrogens here, so it's going to be CHH. So who wins, CCH or CHH? Well, the top one, because it has 2 carbons here. And so like this carbon ties with this one, but then this carbon beats this hydrogen. And so that's kind of one way to think about it. So now we see the highest priority things are both on the top, on the left side and the right side. So we know that they are on the same side, and this is a Z alkene. Now, for this one on the right, let's go ahead and divide our double bond down the middle. And I see carbon versus carbon here. What is D? Does anyone know what this mysterious element thing D is? Have you seen this before? Deuterium. Yes. Okay. So hydrogen, she's our number 1. She's our OG on the periodic table. So yes, she has isotopes, but more so than any other like element. We don't do this for like carbon's isotopes or oxygen's isotopes. We give special names to the isotopes of hydrogen. So normal hydrogen just has a mass number of 1. It's just a single proton. That's hydrogen. You know her, you love her. Hydrogen with a mass number of 2, so a proton and a neutron, we call this deuterium. Deuterium. And then you're rarely going to see this. Like, it probably won't come up for our course, but there also is a H3 isotope that's radioactive, and it's called tritium. I forget if it's a T or a TR. I think it might just be T. But anyway, y'all don't need to worry about her. So deuterium here, she's an isotope of hydrogen. So if we're comparing HHH versus DDD, who wins? Well, they're the same atomic number. They're both atomic number 1, but the deuterium's the heavier isotope. So it's going to be our winner. Now then on the other side, we have a challenge. So we have a carbon up top, carbon on the bottom. We look at substituents. Well, the top one's going to be the exact same that we did over here. We have 2 carbons and a hydrogen, so this is a CCH. But then on the bottom, we've kind of scorched the things behind us. We know that there's an H here, but we have to list out 3 things that this is connected to. And it's kind of weird because we have a double bond. So what we do when we are reaching another double bond, or like a triple bond even, as we kind of go out and do this ranking system, is we are going to count this double bond as a C, and then we have the H that's implied down here. So we count the double bond twice here, and that's how we get our 3 bonds that we have to account for. So CCH for CCH, we are tied. So we have to go 1 more out. So on the bottom, we're looking at this C. But on the top, when we branch out, does it matter if we choose this C versus this C? Those are going to be exactly the same, right? They're both CH3s. Now, slightly harder question. If these were not equal, let's say this was like a propyl chain and this was a methyl change, does it matter then which carbon we choose? Well, in one of them, it would be a HHH over here, and the other one, it would be a CHH. So it's going to have some impact on like our priority ranking. And so if the paths are different at a branch point, we say always go down the highest priority branch. Go down the branch that's most likely going to win when you like compare them. But in this case, again, we don't have to worry about it because it's equal on each side of just a methyl. So let's just choose this carbon. We have carbon and carbon. We said that this top one, the substituents were HHH. And the bottom one, we know that there are 2 H's here. But we need 3 things, right? And like normally we like don't look at anything behind that atom. This is the tricky thing. The only time where you go backwards for a bond to include for the substituents is when you have a double bond like this. So you are going to count the double bond once on this one and once on this one. And by when I say once, I mean like This carbon can be thought of as like the single bond to carbon. This is the pi bond here. And then this one is the pi bond here. But all you need to know is that, like, if you have only two things and there's a double bond, your third thing is just whatever you have the double bond to. So it's just kind of tricky. But with that in mind, now we have an HHH versus a CHH. Our carbon is going to beat the hydrogen up top. So now we have the two on the same side. So it's a Z alkene. Now, what about this alkene? Because we could also do an assignment for this. Is this an E alkene or a Z alkene? Or a secret third option? Well, if we divide it down the middle, and we're comparing hydrogen versus hydrogen, who wins? Yeah. They're the same, right? Like, they look the same to me. So can we declare a winner on the left side here? No. So it's the secret third option. We would say that this alkene is neither E nor Z. And the reason that we can say that is because there is not an ambiguous way of writing this alkene. It's on the end. So there's not going to be kind of a cis in a trans version of it. Like, it's always going to have the hydrogen on the end either way. And so it doesn't matter. Like, there's nothing to indicate. Last one, I'm going to do super quick. We divide the double bond down the middle. On the right side, we have a carbon versus a carbon. On the top, our substituents are N, H, and H, our two little hydrogens here. And the bottom, we have C, N, and H for this carbon, this H, and this N. And so our C, N, H wins because the N's tie and the C beats an H. And then the other side, well, visually I can just tell these are the same, right? Like, this is a CH2 up top, the bottom is CH2. These are going to be the same. These are going to be the same. So it looks kind of crazy, but here it's a tie all the way down. Like, these carbons are going to be identical, these carbons are going to be identical, these are going to be identical. And so this one's another neither. And I don't think that we do it often, of like putting you in the position of like saying that it's a neither, but we want to make sure that you really know these terms and what they mean and aren't just like guessing on some of the rules. So these are most all of the kind of tricky rule things that I see brought up in the main kind of problems on this. And yeah, it's like just learning the rules of the card game of like who wins. So that is our EZ labeling system. Any questions on this before we go on to RNS? Okay. Zoom teaching is so much more awkward than in person. Like, I forgot, like, I think during, like, COVID years, I got at least so used to it. And then I'm just, like, I got so used to, like, just, like, verbal feedback. But thank you for those of you that have your camera on. Like, it's so great to like see your faces of like, or yeah, we're good. Okay, moving right along. So E and Z was our nomenclature for double bonds. And now we're going to talk about our nomenclature for stereocenters. So we want to make sure that we can name, like in the example that you saw in class, some of you built, I think, 2-butanol that looks like this, and some of you built the 2-butanol that looks like this. Well, these are different molecules, and we want to be able to specifically name the one that we're talking about. We want to be unambiguous about which one it is. And so this is what we do. Remember, a stereocenter is a carbon that's attached to 4 different things. First thing that we do is exactly what we did with E and Z. We rank the priority of all the things on the stereocenter. So we assign it values 1, 2, 3, and 4. Once we've done that ranking, we orient the molecule so that the lowest priority group is pointed away from us, typically into the page. And again, this is how the rules were formulated. They just had to say, everyone follow these rules so that we're all on the same page with our naming. And this is going to be a little bit different than what we actually do in practice to figure out the name. So we'll talk about that in a minute. But they say, okay, orient the molecule so the lowest priority group is going away from you. And then trace the priority 1 to 2 to 3. And if, when you trace that, it's clockwise, we are going to just call that R. And if the priority as we trace from 1 to 2 to 3 is counterclockwise, we call it S. Oh, Evan, your question on double bonds, like here, there just isn't another way to draw this if it's neither. So like either way that you draw it is going to be totally fine. And even though this one looks crazy, it's going to be exactly the same. It's going to be the same molecule no matter how you do it. But we can talk more about it later. Okay, so again, we rank things, we orient the molecule so that the lowest priority group goes away from us, and then we trace 1 to 2 to 3. So with that, there are essentially 3 big scenarios, for the most part, that we are going to confront you with. Because the ranking actually of itself, you're going to get a lot of practice with that with both E and Z and R and S. But let's imagine we've already ranked it, and let's talk about the different scenarios that we might run into. So, one scenario I call normal mode. Normal mode is when our lowest priority group is going away from us. It's on a dash. And so, this is exactly what we want for our rules of R and S naming. So we can just do trace 1 to 2 to 3. It's clockwise, so we know that this is an R stereo center. Now, the second kind of case that we could have is we could have our 4 coming out of the plane at us instead of going away. In this case, it is the exact opposite of what we want. And so this case is called opposite day. And you don't really need to think through, like you can prove it to yourself that this works and it is this property. But I really just like being like, oh, it's the opposite of what I want, so I guess it's opposite day. So what we do is bury our head in the sand. We just say, okay, I'm going to trace 1 to 2 to 3. 1 to 2 to 3, it's counterclockwise here, which would normally be S, right? Counterclockwise is S, but it's opposite day. So actually, it's going to be an R stereo center. And so it's really just as simple as that, of the opposite day. One thing that you'll also see that I really like doing to help keep me straight, just like the little stars for alkenes, is I like, after I trace the priority, to just do another one over here that's contiguous, like a single line, a little bit smaller, just so I can like double check the clockwise versus counterclockwise, because if you make one mistake, then you get the wrong answer. And like there's no kind of partial credit on these because there are only 2 options. So just watching out for that. So we can deal with 4 going away from us. We can deal with 4 coming towards us. And the hardest thing to deal with these is what happens if 4 is in the plane. So Serenia is a big advocate of the hand method here, with like putting your thumb in the lowest priority group and tracing the hand. And if it works on your right, then it's R, then left it's S. You know, it works for some people. It doesn't work for others. A lot of like spatial reasoning things, I would say that there are probably like 5 different ways I know, like robust ways that are taught in whole schools of dealing with this case. And like everyone does different things. And if you find something that works for you, great. I'm going to teach you one that I really like, which involves redrawing the molecule. And it's one where I think that it relies on less spatial visual like reasoning. And so in that way, I think it's a little bit more reliable. But I'm just showing you this way so that you'll have another way of approaching it. If you want to do the hand way, that's great. But also me trying to do the hands on Zoom with like the flipped camera and everything, I'm like, that's going to waste y'all's time. So what we do when we are in the plane. And again, for in the plane, we're talking about our lowest priority group, the 4. So step 1 is we are going to grab the molecule by whatever the other thing in the plane is. So here, 4 is in the plane. The other thing in the plane is 1. So I'm going to draw like a little claw that's like I'm kind of holding it from this position. Then what I want to do is I want to think about rotating around this single bond in order to put my lowest priority group where I want it. So in order to put my 4 over here where 3 is. So just already, like that's a lot for the setup. So we're holding at the top, we are kind of spinning around this double bond, and we're putting 4 where we want. So what we do is we draw the bonds exactly like they are on the original molecule. So I've reproduced it down here exactly the same. And which one did not change position here for our diagram? Well, the one that's not changing position is the one that we're holding it from, 1 up at top. So I'm going to put 1 right up here at the top. It stays up there. That's where we're holding it by. And then we just rotated. The whole purpose of this was to put 4 on the dash. So I'm going to put 4 right here. So now we have to think, okay, well, 3 was originally on the dash. Where does 3 go? And if we just trace this path, we see 3 is going to go onto the wedge. And then, completing it one more time, 2 gets translated to the other spot in the plane. And so what we've done with this strategy is we've just redrawn the exact same molecule a different way. We've rotated it to get a different vantage point. And now we are in normal mode. So 4 is going away from us. We can just trace 1 to 2 to 3. That's clockwise, so we know that this is R. And our original structure that we drew is also R because we know that this is just a rotation of the same thing. Rotating does not change our R and S configuration. Rotating just changes how it's sitting. So let's do the same process over here for this other one with 4 in the plane. So we grab it by the other thing that's in the plane. This time we're going to grab it by 2. And then we want to send 4 to the dash position. Okay, so redrawing it with the bonds and everything, 2 is going to be exactly where it was the whole time. We are holding it by 2, and we put 4 now on the dash. Okay, well when we do that, if we keep tracing this trajectory, 3 gets put onto the wedge. And then that is going to push 1 up top. So now we have just redrawn the same molecule. We did a rotation, and we are in normal mode. Okay. So now what I'm going to do is I'm going to trace 1 to 2 to 3, and it's clockwise. So this is R. And ooh, I've done something a little tricky and devious. All 4 of these are the same molecule. I've just drawn it in 4 different ways. All of them were in our stereocenter with our ranking of 1, 2, 3, and 4. And so one thing that you'll kind of see in this chapter is your intuition about how a molecule looks is something that's going to need to be trained because it's not something that's going to be blatantly obvious with the eye when you're working with it. But thoughts on this in the plane rotation strategy, it's a little bit slow, but I at least find that it's one I can do with making fewer mistakes. But also, if the thumb way works for you, go with God, Any questions on this kind of rotation strategy? Ooh, I see one in the chat. The solid wedge has to be in a specific location relative to the dash. Yeah, so the big thing about this redrawing strategy is the bonds have to appear exactly like they appeared in the original. So, if you have it appearing exactly like it did in the original, then this strategy will work for you. Yeah. But, again, more tools for looking at things. So, with this, we have some stereocenters here. And honestly, I'm probably not going to do all of these, unless y'all want me to, just because, I don't know, I still feel guilty that section's, running long, and it's going to run long. I am already, I don't know, 3 or 4 minutes over the current plan, and the plan was for an hour 20, and so I don't want to, drag y'all along with me, kicking and screaming through this, but also, do you want more RNS practice, or are you I got this, we can zoom through? More practice. And then Fallon, I see like a kind of indifferent look of meh. I definitely do not have it, LOL. Okay, cool. Okay. In that case, I will stop making comments about it, and I will just take however long it takes to teach the things, you know? So, first up, if we are assigning a series center, we have to do our ranking, which is the exact same that we were doing with ranking with E and Z. So, we have an O versus an N versus a H versus C. What's the highest atomic number here? Well, the one that's furthest on the periodic table is going to be O. Thank you. So, our priority number 1 is O. If you ever have a hydrogen on your stereo center, hydrogen's auto 4. It always takes the L. Then our next highest atomic number is 2. The place 2 is going to go to nitrogen, the second highest. And then 3 is going to be our carbon. So once we've ranked our 4 things, we ask, what mode are we in? Well, we look at our lowest priority group. It's coming out of the page at us. So we are in opposite day. I trace 1 to 2 to 3, pretend like nothing is wrong, like it's not the end of the world. And I trace 1 to 2 to 3, it's clockwise, so we think it's R. But hey, it's opposite day. So instead of being R, it's actually going to be S. Okay. Well, then we have this second one over here. Well, I have an O, a hydrogen, and then what atom is going to be here for Me and Et? What are these? Some carbons. Yeah. Remember, an ethyl is like a CH2, CH3, and a methyl is a CH3. So these are carbon-carbon, oxygen, and hydrogen. Well, we have an automatic first and fourth place. So our first place, top priority is oxygen. Our fourth place is the hydrogen. And then ethyl and methyl. So this is where you can start taking shortcuts if you are like careful. So like I know that this is bigger and more complex ethyl than methyl. And so it should be that the next highest priority 2 is ethyl and 3 is the methyl. But we can totally do this out like beat by beat. Like we could do, this is CH2 with a CH3. And this is CH3. So you're comparing the carbon versus carbon. The top one is CHH. And then the bottom one is HHH. That is totally fine and valid to be doing that out. And then eventually you'll probably get to a point where it will be easier to just visually check and see. So just do that transition whenever feels comfortable for you and whenever you find yourself making fewer mistakes on like the practice problems. So now we've ranked it. And we have our lowest priority group in the plane. So it's the hard mode. So with this, remember our strategy. We hold it by the other thing in the plane. So we're going to hold it by 1. And then we rotate 4 so that it goes where we want it to be on the dash. So now I'm going to redraw the bonds exactly as they appear. So I keep my angles totally the same for this. What did I keep in the same position? Well, I kept 1 in the same position up top. 4 came down on the dash. And then we continue rotating around. So 2 came up here on the wedge, and then 3 went into the plane. Also notice for this, when I redrew it, I didn't redraw all the substituents. I just did the priority number, because that's what we care about. And also, like, if we just redrew the same molecule, it might lead to moments of confusion where, like, we might have to, like, redo our ranking to double check things. So I think it's just cleaner this way. So now we are in normal mode. We trace 1 to 2 to 3, and it's counterclockwise. So it is S. The last one down here looks weird, but it's not that bad. So all of these are carbons, right? We have carbon, 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 carbon. But do you have a sense which one's going to be lowest priority here? The methyl, the ethyl, the propyl, or the butyl? The shortest one, the methyl, yeah. Because, again, if we just look at the substituents, HHH versus all the rest of these are CHH. And then we can do that for all the others. So we know that this is 4. But then between these 3, if we go 1 out, comparing these, well, this one's next shortest. So this is going to be 3rd priority. And this is going to be 2nd priority. And this is going to be 1st priority. And so again, getting to where you can get these kind of visual shortcuts. So now this one's nice. If I saw this on a test, I'd be so happy. Normal mode. So I don't have to do any more work. I just trace 1 to 2 to 3 clockwise. So this is R. So this was kind of our configurations assignment, like practice here with R and S and E and Z, going through how we label these specifically. And so now let's see how this would probably appear on an exam. So on an exam, we'll do something like practice 3, where we'll give you a big complicated molecule and we'll point to some things and ask like, what's the indication? Like, what is this? EZ, RS, neither, whatever. And granted, I'm going to also say these are hard. So these are going to use some, like one of these is like extra hard to me. So we are going to just take them one at a time and deal with them. Oh, that's all we can do. So let's start with our alkene over here in eplerenone. I'm not even going to try anymore. So we divide perpendicular to the double bond. Now on the left side, we have a carbon versus a hydrogen. There's a clear winner here, our carbon. And then on the right side, we have a carbon versus a carbon. So we list out substituents. The top one is connected to a carbon, and a carbon. CCC. But the bottom one over here is connected to a carbon, and it's connected to 2 hydrogens. So that's going to be CHH. So the top one wins here. CCC beats out CHH. So now we see both of these highest priorities are on the top. They're on Z same side. So this is a Z alkene. Not too bad. Then let's do the stereocenter up here. So we have a carbon, a carbon, a carbon, and an oxygen here on this stereocenter. So the only thing that we can say for sure is that oxygens are number 1 priority, right? Like it has the highest atomic number. So 1 is here. But then comparing carbon, carbon, and carbon, we have to look at substituents, and it gets a little messy. So firstly, let's look at this top carbon. Well, it's connected to this carbon and 2 hydrogens. So that's a CHH. And then this carbon is connected to a carbon, a carbon, and a carbon. CCC. Last one. This carbon is connected to a carbon and 2 hydrogens. CHH. So between these 3, is there one that beats out the others? Yeah, the CCC wins. So this is going to be priority 2. While I do this, I'm also going to get out the answer key to make sure I don't make a mistake. Because it really is so easy to do. But I feel pretty confident in my abilities. We will see. So now we are comparing this chain and this chain, right? And so we have to go 1 carbon out between these 2 because these are exactly tied. So now I'm looking at this carbon up here and this carbon down here. Well, I hate to say it, it's a CHH versus a CHH again. That sucks because we don't get to be done with this stereocenter yet. So we have to go out yet another one and compare this carbon and this carbon. Okay. Well, now the top carbon is connected to 3 oxygens. And the bottom carbon down here is connected to, remember, we can only go, like, we have to burn the entire path behind us as we leave the stereocenter. So this carbon's connected to a carbon, a carbon, and a hydrogen, a CCH. So with this, we have a winner, our triple oxygen. So that's going to be our third highest priority route. And then that would make this our fourth highest priority. So they decided to be mean with the ranking of this. That is what I'm seeing here. This is not kind. But I'm glad we're seeing not kindness here rather than on the exam for the first time. That's better, I guess. And then also, where is not the practice problems, section 3. Where's the section 3 solutions? I don't know. I feel okay. So when we have something that's like this is really, really tough to look at, right? Like we have a lot of annotations already on here. And so what I like to do to just make it a little bit easier for me is I'm going to just rewrite this out down here. The big thing that you have to do if you are rewriting it out is keep the bonds exactly the same in terms of their bond angles. So I'm recreating this stereocenter's bonds. And now I'm just going to replace it with the numbers. So this is a 1, 3, yeah, 2, 4. So now that we can see this, what mode are we in? Normal mode, offset, or in the plane? Well, this is in the plane. So we have to do our rotation strategy or our thumb strategy, whichever you prefer. So what I'm going to do, I'm going to hold it by the other thing in the plane. And then I'm going to rotate it. I'm going to rotate it to send this 4 to the dash position. So I'm going to redraw this one more time. Again, keeping the bonds in the exact same spots. 2 is what we're holding it by. And we're yeeting 4 over to the dash. So then we rotate around and 3 gets put on the wedge. And then 1 gets put in the plane. Now we are finally in normal mode. And so 4 is going away from us. We trace 1 to 2 to 3. 1 to 2 to 3 is clockwise, so we know that this is an R stereocenter. See what I mean about these being like super hard? Like there's a lot of work going into this. And the last one here is like miserable in its own like separate way. It's not like tedious bad in terms of all the ranking with all this, but just not a kindness to the spirit. And I found the answers and we were right. Ooh, love that. Love that for us. Okay, last one. So we are looking at this stereocenter right here. And already alarm bells should be triggered in your head. Because look at the bonds here. 3 of them are drawn as in the plane of the page. And only 1's on a dash. When normally we have 2 in the plane, 1 on a wedge, 1 on a dash, right? Well, I thought this whole wedge and dash nonsense was because the tetrahedral structure of sp3 hybridized atoms. So something's weird here, and the weirdness is really our notation. The thing to think about is like in the way the molecule is actually sitting, these are chairs. They are going to have their own like 3D structure, and so this is just a weirdness of the notation to deal with. But nevertheless, we will still plow ahead with ranking the priorities of the 4 things on it. So I will use obnoxious colors now. We have oxygen, carbon, carbon, and carbon. So we have a priority 1 at least, our oxygen. Then we are comparing carbon, carbon, and carbon. And we do the substituents. So the top carbon, it's attached to a hydrogen an oxygen, and a carbon. And those are, we have a hydrogen there, we have oxygen here, and we have carbon. This one we already ranked. We said it was CCC. And this one, remember, we burn everything to our stereocenter. This is connected to a carbon, and a hydrogen. So this is going to be a CCH. Well, at least we have clear winners here. We don't have to go out any further. So between all of these, the next highest priority is going to be this top one. And it's because we have an oxygen. So oxygen's the highest atomic number. It's going to win. Then third up, we have carbon, carbon, carbon. Because that last carbon is beating number 4 over here, carbon, carbon, hydrogen. Already I'm just in it, and I'm like, I hate it. I'm so sorry. Let's do the exact same redrawing strategy that we did for the first one, because right now it's really messy and hard to look at. So what I'm going to do is I'm going to draw the bonds exactly as they appear in the molecule. And I'm going to replace what actually is on the molecule with numbers. So this is my 1, this is my 2, this is my 3, this is my 4. So now, when we are in this, our redrawing rule doesn't really work unless the 4 is going away from us. Our 4, normal mode does not really work, or opposite day. And so thumb, if you can do it, this, if you stick your thumb in 4, you can trace it, you will get the right answer. But the way that I see this one most clearly is if I imagine a Newman projection. So what I'm going to do is I'm going to imagine that I am looking at this thing from an eyeball that is situated over here. And when I do that, like a Newman projection, I'm going to be seeing kind of a Y right here. And that's from these 3 things that are on here. So it is a normal Y. It's not an upside down Y, because again, this is going straight down relative to the eye. And these are going up. And when I do it this way, I see it's 1, 2, and 3. If we know that this is dashed going into the plane, that's going to be on the left side of our eye, which means that this, even though it looks straight up, it's going to be kind of to the right of the eye. And so really you can think of this bond as being a little bit on a dash here. That's one way to think about this. The best way to really kind of see it is to think about chairs and build a chair, but honestly, it's a really tough one. Now, why did I choose to look at the molecule from this angle? Well, this is the angle where 4 is going away from the eye, right? The 4 is going to be exactly opposite the eye's gaze here. And so we can just trace 1 to 2 to 3 here and get our stereocenter. So here we trace 1 to 2 to 3, it's clockwise. So this is an R stereocenter. Woof. Woof. So we can see how these RNS-EZ can be easy and they can be hard. And this is why doing practice is the best thing that you can do for these, because it exposes you to all the tricky things that are going to come up. Yes, and this is also why I didn't want to just start off with this, because all of these examples, other than the alkene, the 2 stereocenters were really challenging. And I want to clock that these are challenging. Whereas these are kind of the more straightforward, we're getting our sea legs of how do we do this? There's one more part of this that says draw the enantiomer, but let's wait to do that until when we've talked about what enantiomers are. So any last questions on this, practice 3 or easy RNS things? I know we spent a lot of time on it. Cool. So moving on. So we have a lot of vocab terms in this lecture and last lecture. And really, I feel like they're best identified with a tree. I think Serenia has a version of this, but again, you know how I like to yossify the things in class. And really, these terms are just going to help us describe kind of 3D structures of molecules. So first off, we have the umbrella term isomers, compounds that have the same molecular formula, but are different compounds somehow. And so our first type of isomer are constitutional isomers or structural isomers. These are isomers where we have just fully connected the atoms in a different order. So like here, all the carbons in the middle are connected to 2 carbons on either side, and then there's 1 on the end each. It's like a straight chain. Here, we have a carbon that's connected to 3 things. It's a fundamentally different connectivity. In this one, you have a carbon connected to 3 other carbons, I should say. In this one, you only have carbons connected to 1 or 2 other carbons. And so we plugged it in differently. So these would be structural or constitutional isomers. One thing to notice with this is they both have the exact same molecular formula, so they're still in that isomers camp. They're not just wholly different molecules. Then, if molecules are connected in the same way, we are in the family called stereoisomers. These are isomers that have a different 3D arrangement of the atoms, but the same fundamental connectivity of like what atoms is it attached to. The difference is in how they're laid out in 3D space. So for stereoisomers, we have 2 types, and only one of them has a good definition. So the one that has a good definition is enantiomers. So we talked a little bit about this with chiral, where we were kind of taking mirror images and trying to superimpose them. We talked about our hands, kind of laying them on top, and our hands are mirror images, like mirrored, but they are non-superimposable. We can't like lay them flat and have them exactly overlap. And so the definition of enantiomers are molecules that are non-superimposable mirror images. And if we are a chiral molecule, we will have an enantiomer. So remember, we said that if we had 0 stereocenters, then it's achiral, 1 it's chiral, and then 2 or more we have to check for meso. This one, these 2 stereocenters are different, so we don't have to check for meso because there's not going to be a plane of symmetry. If one's nitrogen, one's oxygen, they would have to both be like oxygens, both be on wedges or dashes. But when we do this mirror image thing, here is our mirror image. We did the mirror image of a chiral molecule, and so this will be non-superimposable for our original. Hence, they are enantiomers. But one really useful thing to notice about this is these original stereocenters were R, and in this mirror image, in the enantiomer version, they are S. And so one feature of enantiomers is all the RNS swap. So now, I'm going to make a fool of myself because, again, I can't force y'all into Pavlovian conditioning call and response like I can do my summer class. But to help you remember this, I have made a little, I won't call it a rap, maybe a jingle. So bear with me, and I'm going to do it about 3 times until it gets stuck in your head. And if you want to like follow along, by all means. If you want to roll your eyes, if you want to leave down, by all means. So I tried to like emphasize it here with the text. 1, 2, ready, go. Enantiomers. Non-superimposable mirror image. Enantiomers. All swap. So that's the chant. I'll do it a little bit slower if you want to try to do it with me. And again, it's just incorporating these 2 definitions of enantiomers that you'll want to have this definition like locked and loaded. So a little bit slower. 1, 2, ready, go. Enantiomers. Clap. Clap. Non-superimposable mirror image. Enantiomers. Clap. 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 All swap. I know it's a little silly. I appreciate you for bearing with me. I'll do it one last time, kind of full speed. And again, feel free to join along. No pressure. 1, 2, ready, go. Enantiomers. Non-superimposable mirror image. Enantiomers. All swap. So those are 2 ways of drawing enantiomers. And we'll get some practice with actually doing the drawing of this in a minute. But that is our like good definition that we have for a type of stereoisomer. And then the other type of stereoisomer that we have is called the diastereomers. And it is what I affectionately call the junk drawer. It is just everything else. So if the 2 molecules are stereoisomers of each other, they're like different molecules, but they're not enantiomers, well, we put it in the junk drawer, and we call it a diastereomer. So there are 2 kind of fundamental things that you will see in diastereomers. One is where some, but not all of the RNS swap. So here, this OH version is going to be the same. R on both, but then the nitrogen swaps from R to S. Well, we know an enantiomers all swap, so this is not an enantiomer, so what is it? We put in the juncture, diastereomer. The other thing that falls into this, which is kind of counterintuitive, are alkenes, like E and Z isomers. Because like they have the same connectivity. This carbon is connected to a carbon, a hydrogen, and a double bond carbon. This carbon over here is also connected to a hydrogen, a carbon, and a double bond carbon. So we are attached to the same thing, same connectivity, but they clearly have a different 3D arrangement in space. And so they are diastereomers. They are in the juncture. What are the superimposable mirror images called again? So if it is superimposable, you have just formed the same molecule. So they are like just identical. And when we were talking about chirality, and this is like a kind of test or criterion for chirality, we said if we generate the mirror image of a molecule and we can superimpose it, then this is achiral. But moreover, it's the exact same molecule because we can exactly perfectly overlap it. So like this and this are the same thing. Ding dong. Okay. So that is our like tree of all of our isomer terms. The last thing I want to touch on super quick is conformation and configuration. And the big idea here has to do with like interconvertibility. So conformations, think about it as like it is something that can be readily interconverted to. So Newman projections, when we were rotating around bonds, those are different conformations of the molecule because we can rotate easily between them. The redrawing of stereoisomers that we did, those are different conformations of the molecule because they really align to the same kind of Newman projection rotation. Ring flips are also conformations. An important thing about different conformations is they can have different stabilities here. So some conformers are going to be more stable and some are going to be less stable. Think about it as conformations are how a molecule is sitting. Meanwhile, configurations, these are about the arrangement of atoms in a molecule that cannot readily interconvert. So this is going to be like the difference between an R and an S. If you have a model of an R version and an S version, the only way that you are going to be able to get from the R to the S is if you literally unplug atoms and plug them in different spots. So they do not interconvert at all between them. And so we say that these are different configurations. It's kind of like the hard wiring of the molecule, like how it exists. And here, like E and Z are the same thing. In our dog metaphor, like this is our good dog Spike. This is an alien that has invaded. It's a different configuration of Spike, but it is certainly not Spike. It is something else. Whereas in this, they're both Spike, but in one of them, Spike is like calm and stable, and the other one, Spike is not doing great. Upshot, the TLDR. Conformation is how she's sitting. Configuration is who she is. So, like the actual identity of the molecule versus just how it's sitting. Moving on to this skill that kind of puts all these terms together. And again, this is the one where we do not have a section problem for it, but I think it's honestly the hardest thing for this lecture. And you have a couple of pages on the problem set about it. And so one thing I want to do is kind of talk through some like concrete tools for approaching these types of problems. The essential setup here, and I've called this type of setup discerning stereoisomers, but what it's going to be is we are going to give you two molecules. We'll print two molecules side by side on a page, and we will ask you, what is the relationship between those two molecules? Are they the same molecule? Are they enantiomers, diastereomers? Are they constitutional isomers? Are they completely different molecules? Like, that is a kind of hard thing to do, both in terms of all the vocab and also in terms of our visual spatial reasoning. And so what I'd like to do is kind of talk you through all these different questions that you might ask yourself for a couple of molecules, and then talk through like what to do in that case or how to check. So first thing to check is, do the molecules have the same molecular formula? Like, for example, the core ring here looks the same in both of these. And then it looks like we have methyls here, a methyl and a hydrogen. But like if instead I had a propyl, are they going to have the same molecular formula? Well, no, this has more carbons. And so that's just a reality check. First thing to do, are they isomers? And yes, they appear to have the same molecular formula. So we know that they are some type of isomers. And then we ask our first question in our kind of branch over here, do they have the same connectivity? And here we have a carbon that's connected to a nitrogen, a hydrogen, a methyl, and then another carbon. But here our carbon that's connected to the nitrogen is attached to 2 hydrogens in a carbon. It's not connected to a methyl. So this tells us that we have just different connectivity. It's like we plugged in the methyl to a different spot on the molecule. So these are, if the answer is no, structural isomers, also called constitutional. So then let's say that we have checked, like imagine example 2, we have checked they are the same formula, they are the same connectivity. Another question that we might have is, are these the exact same molecule, just drawn in a different way? And one really powerful tool for doing this, of figuring out if 2 things are the same molecule, is called a pancake flip. So imagine you have like a pancake in the skillet, and you're cooking it, and then you are done cooking one side and you want to cook the other side, and you go and flip it up in the air, and like the bottom of it that's on the pan side goes and now is up top. Oh no, I've frozen. Hello. Sorry, I froze. So the bottom of the pancake we now flip over and is now going to be on the top. So let's think about this with things like dashes and wedges. So let's imagine that we start off with this molecule and we are viewing it from above. So like our ring is going to be flat. And my OH, that's a wedge that's kind of coming out of the page, I'm going to view that as going up. So if I do a pancake flip and turn this over in the air, do you see how now it's going to be going down? Like the up, but then when I pancake flip it, it's now going to be down. So when we redraw the molecule after doing a pancake flip, this OH that's on a wedge is going to be on a dash. But also let's think about it kind of being like a storybook thing. So like if I have blah, 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 this over here, where my like fingers are on the side, and I pancake flip, now my fingers are on the other side. So like, again, fingers on this side, pancake flip, fingers are on the other side. So this carbon, when we do our pancake flip, is actually going to move all the way over here. And our wedge, because it was out of the page, is now going to become dash and going into the page. Likewise, if we started out with something on a dash, kind of going away from us, and then we flipped it over, when we pancake flip it, it's now going to be on a wedge. It's going to be coming up towards us. So pancake flips, again, we are not starting and making a new pancake when we flip it. We are just figuring out the like drawing tools to show what would this molecule look like if we flip it 180 degrees. Kind of bring it up off the page and fold. Then we can do things like rotate it, and you can do other pancake flips. And I've tried to just give you a kind of annotated example for you to check on your own to show that all of these are the exact same molecule. That I just rotated it and pancake flipped it and see the different ways to transform it. So I'll let you like go through that on your own. But let's try to do a couple of quick pancake flips. So for this one, I'm going to try pancake flipping across this line. I'll write PF here to say I'm doing a pancake flip. Well, I know I'm still going to have the square at the end of the day, right? But let me start off with this star that has the bromine. Well, now, if I pancake flip it, it's going to be on the opposite side. So the star is going to be over here. Then same thing over here with the circle that has the methyl. And then the triangle, which was on the outside, I guess. If you flip it over, it's going to be on the other side completely. So we mapped our carbons for a pancake flip. And then we just need to know that they're going to have the same substituents, but you change the wedge and dash. So for star, our bromine was on a wedge. Now our bromine's on a dash. For circle, our methyl was on a wedge. Now it's on a dash. And then for triangle, the ethyl was on a dash, so now it needs to be on a wedge. So I've just drawn my pancake flip of the molecule, and this is another representation of the exact same molecule. Like I've just drawn the same molecule a different way. And another one that I'll do down here, if I do a pancake flip, well, I'm going to still have the same chain, but then this one that was one from the end on the right side of the molecule now becomes one from the end on the left side of the molecule. And then the one next to it, which was in the middle, is in the middle on the other side for the pancake flip. Then we swap the wedges and dashes. So the OH is now on a wedge, and the Cl is now on a dash. These are the same molecule when we do our pancake flip. So now let's see why that's helpful to have this as a tool in our repertoire to do. So going back to this example, these look pretty similar, right? Well, let's do a pancake flip and see if we could redraw one of these in a way that is helpful, or lets us compare it well with the other molecule. So what I'm going to do is I'm going to pancake flip it around this axis. So I'm going to go for my triangle being over here, and this is going to look bad for a minute, and then I'll move it. I'm trying to see what will most stand out. It is going to go like this. And the thing that is most close to it for the pancake flip side, it stays close. Or the thing that's, I guess, rightmost becomes leftmost. Then this one would go over here. And the square one up top stays the same. And with that, I'm going to go ahead and just now that we've mapped it, move this down just to give it a little bit more space. So now I just need to swap the wedges and dashes of everything. So circle and star both had methyls, but they were both on dashes originally, so now they're both on wedges. And then the square had an ethyl that was on a wedge, so now it needs to be on a dash. So I have just redrawn the same molecule as this right one. Now this to this. And now that we've redrawn it this way, we can see, oh, this is exactly the same as the left original molecule that we had, right? And so we know the relationship between these two molecules, they are the same. Are they the same molecule? Yes. And a pancake flip is going to be your primary tool to try to check if things are the same, to redraw them in a new way and compare it. Questions on that? Because I know the pancake flip can be a little bit hard when you're first trying it out. And also, if anyone has questions, you can feel free to unmute for the question or in the chat.
I'm sorry, I have a quick question.
Please.
So, for the methyl group that's attached to, the new mirrored image, that dash, doesn't it goes to the opposite side since it's a pancake flip?
Yeah, this methyl over here goes to this side.
On the top.
Oh, this one
was originally attached to a wedge.
I see what you mean. Why don't we draw it like this?
Yeah.
Well, what do we know about these single bonds? Well, single bonds we can rotate freely. That's the whole kind of configuration versus conformation thing that we were talking about a minute ago. So I could easily write it like this or like this, and they are the exact same molecule because I'm spinning around a bond that is a single bond that is not a stereocenter. Whereas these three spots we have to treat really carefully because these three spots are where we have stereocenters and where we have to make sure that we are keeping that configuration intact.
Got it. Thank you.
Work. Totally. Great question with it. Work. Now, one thing that you said, Melody, when you chimed in on this, is you said the mirror image thing. So one thing I want to really, really kind of caution is the pancake flip looks really similar to a mirror image, but it differs in one key way. And we're going to get to this here when we talk about drawing enantiomers. So remember we had the two definitions of drawing of enantiomers. We had the non-superimposable mirror image, and we had all swap. Well, that gives us fundamentally two ways of drawing the enantiomer. So when we draw a mirror image, we keep everything the same distance to the mirror plane. So this is our mirror. And so our green carbon that's close to the mirror is going to stay close to the mirror. Our yellow carbon stays close to the mirror. But the important thing is when we do a mirror image, we do not swap any wedges and dashes in our actual drawing. So this is now an OH here. This is now an NH2 here. But they are on dashes. However, if we did a pancake flip to get the same molecule, when we did that, this would be on a dash for the OH and a wedge for the H2N. And so that's just a careful thing to like watch out for, that here, pancake flip, we are swapping the wedges and dashes, and that's allowing it to be the same molecule. Like if you did the R and S assignment of all of these, you would see the O's assignment and the O's assignment here exactly match. However, if we don't swap the wedges and dashes, we are going to go and get the opposite stereochemistry. Like I can just confirm here really quick. This is priority 1, the hydrogen is priority 4, it's priority 2 and 3. This is normal mode. We trace 1, 2 to 3, it's clockwise, it's R. Over here we have 1, our hydrogen is 4. Then we have 2, then 3. Normal mode, again, we trace 1 to 2 to 3, it's S. And so this is also why I like to start with R and S and E and Z, is because if you ever get confused on some of these, if push comes to shove, you can assign the R and S, especially with like a simpler molecule or like a smaller molecule. It's not too overwhelming. So that is one way of drawing enantiomers. And sometimes this mirror image way is going to be really easy and good. But another way, just to have more tools in your pocket, is keep the carbon backbone exactly where it is. So we're going to keep the yellow and the green on the right side now. And now, keeping the backbone exactly where it is, we're going to swap all the wedges and dashes. So we're going to put the OH on a dash and the NH2 on a wedge. Both of these processes of like the all swap and the mirror image, these generate a new molecule. And I'm going to write this out in like all caps. And that new molecule that we generate is the enantiomer. Versus the pancake flip just provides a new way of drawing the same molecule. So when you are doing all these tools, you really are going to want to be careful in terms of thinking about, when I do this, am I drawing a new molecule or the same molecule? And then thinking about like what their relationship is. I also have another diagram here to kind of help you like with mapping some of these out of mirror images and everything, just to see that they are different molecules. So I'd encourage you to like work through this one a little bit more on your own. And I skipped over this, like, are they enantiomers, just because the drawing seemed like really a natural kind of next step. But these are just a kind of like verbally talking through in like, not verbally, textually talking through all the things to do if you're trying to determine if two things are enantiomers. These other ones, I'm just going to skip. Essentially, if all the other things fail and you realize that some but not all of them swap, or that they are EZ isomers, stereoisomers, then they go in the junk drawer, they're distereomers. And then these, I have some just like tricky extra ones to try out. And so I would encourage you to try them and then let me know if you have questions on them, or if you are like confused about it. But again, feel free to like send an email or something about it. This is this kind of discerning stereoisomer skill, and I think that the mirror image and the pancake flip are going to be really invaluable for those like PSET questions. Any questions on this before we do our last thing with chairs? Also, so I'm going to go off script for a second. There is an ice cream truck outside, and the music is the creepiest thing I've ever heard. And it only comes on Tuesdays, and now I'm guaranteed to be here on Tuesdays, And so I have to be subjected to the creepy music outside of this like ice cream truck. My goodness. Ugh. Okay. So, let's get chairs. Our last thing. So, meet the chair. Oh. The chair is going to be our main structure for how we think about 6-membered cyclic rings. And I think about like, ooh, the chair, like the claw. Like, she's going to be an iconic figure. She is going to be someone that you are going to draw many, many a time. And you need to very explicitly memorize this. And when I say memorize this, you need to be able to draw the actual chair. And also you need to know like the exact angles of all the bonds going off of it. Like this carbon in a chair, it only is going to have things at these 2 bond angles. So if you do something on an exam, like you draw a chair, that was not a great chair, and you drew a substituent like this. Do you see how that's not a bond angle for this carbon? This doesn't get any points. Sad. So sad. But again, you're going to just draw this a bunch of times and you're going to ingrain it. There are technically 2 different base chairs, but to be so honest, I've scanned my way through a decade of organic chemistry only really knowing one really well. Like I can do stuff with the other ones, and so I would say pick one chair and get good at it. And then if you want to do the other one, you can. But let's talk about some kind of key features here. Well, when we have a chair, we can imagine a perspective where there's this kind of God eye looking down at the chair from above. And if we look at the chair for any given carbon, do you see how one of the positions is going to go towards the eye and one of them is going to go away from the eye? Like this one's going up, this one's going down. For this one, this is the one that's going kind of up and this one's going kind of down. And so each of these substituents on the ring, we can either talk about it as being an up substituent. So like all of these light blues are up and all of these kind of rich greens are up. Or we can talk about them being down. Here, these are the like slightly off shades from all the others. So that is one criterion that we can apply to each position of like the up and down at each carbon in the chair. But the other thing is whether or not it's going to be perpendicular straight up and down to the chair, in which case we call these axial substituents, or if they are going to be going outward from the chair, almost kind of like a hula hoop or something, or like I don't know, skirt. These are the equatorial positions. And so one thing that you'll notice with this up and down nomenclature and this axial equatorial nomenclature is we have some axial up positions and we have some axial down positions. And then same with equatorial. We have some equatorial up and we have some equatorial down. And this is the thing that I feel like is not explicitly said in lectures enough, like not just our lecture, but every time that this is taught. In a generic chair, you need to know what the up, down, and the axial equatorial is. Like if I circle this in the chair, you need to know that this is an up axial carbon. If I circle this one in a chair, you need to know that it's up axial and down equatorial. And so be thinking about that as you are memorizing these. It's not just something that you assign later. It's, oh, the top right position is up axial. And then it alternates. So if you can like lock in one of, I know that this is an up axial position and down equatorial, well then it swaps. The ones next to it are going to be down axial. Then we're going to have up axials and then a down axial. And then from there, for the equatorials, you can swap it from the original here. So this was down equatorial, so we know this has to be an up equatorial. This has to be a down equatorial, up equatorial, down equatorial, up equatorial. So essentially, what I'm saying is don't like brute force memorize. Memorize this in a really strategic way to save yourself some time and energy of thinking about these ups and down positions and equatorial and axial positions. Now, the most essential skill for a chair that you need to be able to do is to convert between a chair structure and a perspective drawing and with wedges and dashes. Like that's going to be the core thing. It's a PSET question. It'll definitely be an exam question. It's like the classic skill. So the first thing is going from a chair to a perspective drawing with wedges and dashes, and that's going to be the easier option. So what we do is, if something is going up, then we put it on a wedge. And remember, up is relative to this kind of god eye that's looking at the chair. So up goes on wedge, down goes on dash. So we are going to just arbitrarily assign this carbon to one position on the ring, the hexagon here. And the big thing that we need to be careful with assigning our carbons is we need to make sure that we go in our clockwise order. So like B, if we assign our green carbon up here at the top, then the carbon that has B on it needs to be clockwise to that. It needs to be right here. If you put the B on the left side of it, you are forming a different molecule and you'll get points off. And so really just be conscious of like looking down at it, this is clockwise. And then if you're looking straight on this ring, this is clockwise. Okay. Well, A, we said is up, so it's going to go on a wedge. Then B, well, this position is up equatorial and down axial. So that B is going to be down, so it's on a dash. And finally, we skip one, and then C. This carbon is up equatorial and down axial. And so this C is going to be going towards the I more so than the other position. So it's up, and then it's going to be on a wedge. Is that okay so far for this going from chair to like dash and wedge? I think that's going to be the easier way. Okay. So now let's do the opposite, where we're going from a wedge and dash drawing to chairs. Well, fundamentally, there are two distinct chair conformations that we can draw. Like, we can draw the chair so many different ways. Like, for example, I could assign this green carbon here, or I could assign it here, or here, or here, or here, or here. And, like, each of those are going to look different. But the big thing that we ask you to do is to draw the two distinct chairs. So two chairs that are fundamentally different from each other. And this is going to be the hack way to do it, that gets you there all the time. So, if you're going from perspective drawing to a chair, you start off with assigning your first carbon, the green carbon, wherever you want. It does not matter. And then you use your rule that wedges are going to be up and then dashes are going to be down. So if we assigned the green carbon here, we know that this carbon on the chair has these bond angles. It has an up axial and a down equatorial. And so my A is on a wedge in the original drawing, so it needs to be up over here. So it's going to go on this up axial. And then one thing that I think is really good form, and it helps prevent you from making mistakes and getting points taken off, is just write a hydrogen on the other one. And it just helps keep you honest with your bond angles, because again, if you get into a situation where you draw something like this, that does not earn points. It's ambiguous whether it's axial or equatorial. So you have to be really specific with those bond angles. Okay, then we go clockwise around here. And the next one, we know that the positions on this carbon in the ring are up equatorial, down axial. And the way we know that is from our memorized chair drawing. So with that, our B is on a wedge, so it needs to be in the up one. And so the up position on this one is going to be the up equatorial. And we'll put hydrogen down. Last one, again, the memorized positions on our chair. We have up axial and we have down equatorial like this. So C is going to be down here and H is going to be here. And again, we put C on the down position, whichever one it is for that carbon, because it's dashed. So that gives you chair number one, which is fine and dandy and great. Chair number two, what we do to make sure that we are generating a distinct chair conformer from the first one we did, just assign your first carbon, the green carbon, one clockwise from what you did originally. So if you first assigned it here, and the second one assign it one to the right. Let's say you first, in this first molecule, assigned it here, Then in the other chair, you would assign it 1 over. And we'll see what happens when we do this. So I'm just going to go ahead and write in the bond angles for these positions. And for the students who have like just come in, I'm just wrapping up section things, so it'll just be a minute, and then I'll be happy to answer like office-hour questions. So thank you for your patience. So I've just drawn in the angles and the positions here. And again, I do my same thing of if it's wedges, so the A and B, they need to be on the up positions for those carbons. So A and B are up here. Remember, that's up relative to this eye, the kind of God eye looking down. And the other ones are hydrogens there. And C needs to be down. So it's going to be down axial here. And we have our hydrogen. So with this, we have generated 2 distinct chair conformations. And the difference here lies in what's going to be axial versus equatorial. So in this left drawing, how many non-hydrogen things are axial? Well, that one's axial, but then these are both equatorial. And we don't care about hydrogens. Hydrogens are just kind of like neutral. They don't have an energetic cost. So this has one thing axial. First, this one on the right, it has both B and C axial. 2 things axial. So the classic question that we asked here with chairs is we'll give you a molecule and we will say draw the 2 chair conformations or 2 distinct chair conformations for this molecule and then say which one's more stable. And so the last fact that we need to be able to say which is more stable is related to this idea of diaxial strain. Essentially, if we put anything axial that's not hydrogen, it's going to start bumping into the other axial things. So like imagine we have a carbon here, and it has 3 H's, like a methyl. And we have a carbon here, these have 3 H's. These hydrogens are going to bump into each other. And that bumping into each other is going to have steric repulsion. And so that's going to be unstable. Whereas if we put things equatorial things have much more room to spread out. And they're not going to be bumping into things in the same way that these axial positions are going to be bumping into their things. We similarly have diaxial interactions on the bottom, so like between these 3 positions. But just generally speaking, it costs energy to put things axial. Just like it costs energy to put things eclipsed or gauche. So, which one's going to be more stable, having 1 thing axial or 2 things axial? Generally speaking, 1 thing axial. So this is going to be the most stable chair. And the other one's going to be less stable. And again, it depends on the size of the things. So like imagine your 1 thing axial is like huge. Imagine it's a tert-butyl, which tert-butyls don't sound huge to y'all, but they are humongous. Those are like 9 different atoms, or like 10 different atoms really. Versus like here, what if we just had 2 methyls being axial? For this, because they're different sizes, they're hard to compare, so we'd have to give you some concrete numbers about the size and the energetic cost. But with that, this is the fundamental skill. So what I think I'm going to do is I'm going to stop here, and then at the end of office hours, I might record something that just goes through these last 2 practices. But that is the majority of what I wanted to show you with chairs. Then, like practice 5 here is the exact exam type problem that I mentioned. Of we have a perspective drawing, draw the 2 chairs associated with it, and see which one's more stable. Practice number 6 is a little bit more conceptual. It gives you a molecule and says that the 2 chair conformers for it have comparable stability, which is a bit surprising, and it asks you to explain that. So I'll probably record like a little thing, a little ditty after my office hours for it. But with that, thank you for coming to section. Thank you all for engaging. I really appreciate you. And I'll be sticking around for office hour questions. Bye. Okay. Hi, hello. I formally ended my section, but I'm going to keep talking through these last few practices. So one thing I want to get at here is ring flips. So remember in this exercise, we talked about generating these 2 different chair conformations. Well, there's a way that you can do this by starting at one and generating the other. And this involves drawing a chair 2 different ways. One version looks like this, and the other one looks like this. And it's kind of about where the pointy bits are. Like here, the pointy bits are on this diagonal, where here, the pointy bits are on this diagonal. And this is the thing. For some classes, they make you do this version of a ring flip. They make you, like, you have to do it this way always. Our version is functionally equivalent to a ring flip, even if it doesn't do this exact transformation with the 2 different chairs. So the big thing with a ring flip is anything that was axial in one becomes equatorial in the other, and anything that was equatorial in one becomes axial in the other. And when we do this strategy of assigning our green carbon to either this position or the one right next to it, we are doing that fundamentally, because in one of them it's going to be up axial and the other one's going to be up equatorial. Now, this also demonstrates why it has to be the carbon right next door. Because let's say we assigned this green carbon to this position instead. So one that was like skipped one and went over here. Well, in this position, this is also up axial. So we're not going to get that same different rearrangement. If we assign A to be here and then build out the rest of the molecule around it, we're going to get a chair that's like functionally equivalent to this chair that's just drawn a different way. So ring flips there. And this is kind of from the way I have taught this class in the past, or like TA'd this class in the past, is we've always kind of told students that tert butyls are always going to be equatorial. They're going to lock the ring. And that's because tert butyl groups are so bulky that they are going to bump really heavily into these other axial components. And we call this diaxial strain. I'm not sure if I talked about diaxial strain that much in the actual section video. But with that, it has one of the largest A values, which is our representation for how much energy it costs to put something axial. But after I say this, I'm seeing in some of the practice problems that we have, even on this page, and in the problem set, they are doing some questions that make you mess around with the idea of, does it always have to be axial? Does tert butyl always have to be equatorial, or can it sometimes be axial in some rare cases? And so you'll get to see that in some of these problems. But let's do this kind of first problem, practice number 5, as a classic chair problem. Like this would be a great kind of exam level chair problem. So what we're going to do is I'm arbitrarily going to label this my green carbon. And in one of the chairs, I'm going to put that in the top right, and then the other, I'm going to put it the one right next to it. Okay, well, I know my positions on the chair. There are my substituents for both of these. And the ethyl here is on a wedge, so it needs to be up. So in the first chair, the up position is like this. And the second chair, the up position is like this. It's equatorial in this one. Okay, well, then we're going to go clockwise. We're going to skip 1, we're going to skip 2. And then we're going to get at yellow. So I'm going to skip 1, skip 2, and then be at yellow. And same thing over here for this other one. Skip 1, skip 2, be at yellow. I draw the bond angles from just the standard chair that I memorized. And then the chlorine's on a wedge, so it needs to be the up position in each of these. And again, for clarity, I'm going to put hydrogens in the other one just so it's unambiguous. Okay, and then one more clockwise around the ring is our tert butyl over here. So clockwise, clockwise. Now the tert butyl is down. So I draw out the substituents on both of these. And here the tert butyl is equatorial down, and on the other one it's axial down. And we have hydrogens. Now this is a little bit bad notationally. They kind of like butt into each other when we're drawing it. But then we've fundamentally generated there are 2 chairs that we need. So then we just need to see what is most stable. Well, this version has one thing axial, whereas this one has 2 things axial. Moreover, one of the things axial over here is a tert butyl, which is one of the most energetically costly things to be axial. So which one's going to be the most stable? It's going to be the one with the fewer axial things or the smaller axial things. So this is the most stable chair. Then, moving right along, practice number 6 here. Draw 2 distinct chair conformations for this molecule. Surprisingly, they're of comparable stability. So the weird thing here is we have an oxygen in our ring. So I'm going to take that as kind of my green carbon starting position. And I'm going to put my oxygen here in one of them. And I'm going to put it here in another. Again, you just need to make sure that they're on different types of carbon. Like this is on an up axial carbon, this is on an up equatorial carbon. So that's my green. And the way that my original ring is going to work, I'm going to skip one. Then I'm going to have purple and yellow. And again, that's going clockwise. So skip one. Then I have purple. Then I have yellow. And then another skip one. And I have blue. So then I'm going to skip one and have blue. So that's just assigning the carbons in the original to this. And now I'm going to draw in all the bond angles for everything. So this is just from my standard chair. And by the standard chair, I mean literally this thing right to the left, just memorizing those positions. Okay, so now everything was on a wedge. So everything needs to be placed on the up positions. So the purple up is going to be our tert butyl and our tert butyl. Or wait, sorry. It needs to go up, right? So on this carbon, the thing that's up is the axial, but on this carbon, the up thing is equatorial. Tert butyl. Then on the next carbon, the yellow, our up position is going to be the methyl. So that's the up position for each of these. And then lastly, for the blue one, the up position is going to be the methyl. Okay, so we built our 2 chairs. Let's highlight the things that are axial. Well, here the methyl's axial, the methyl's axial. And here we have the tert butyl axial. So there are kind of 2 ways that I would think about this. Normally we would think this is way less stable, right? Because a tert butyl being axial is no good. It's going to bump in to the other diaxial things. So these are our diaxial positions. But one way to think about this is, yes, we are going to have a diaxial like up hydrogen here, and that's going to be not good. Like these are going to bump into each other. But over here, in the axial up position, we have a lone pair. And a lone pair does not have the same diaxial interactions as like a hydrogen does. In fact, like the lone pair, that's just space for our electrons to exist. And so we don't count that as like an energetic cost. So there is no energetic cost here. So like no cost. I don't know a good symbol to do for that. Whereas over here, all of our axial things are going to have energetic costs with the hydrogen and with each other. So like we'll have diaxial interactions here, here, and here. And so even though this one thing is huge, there are fewer diaxial interactions because there is a lone pair here. And then over here, even though these things are smaller, there are more diaxial interactions. And so that is why these 2 are going to be roughly similar in energy level. The other like example, like I think the answer key explanation version, the thing that it brings up here is that this tert butyl is actually a structure that looks kind of like this. And lo and behold, this and this are also diaxial to each other. So the methyl up top there is going to hit this hydrogen here, making this one, even though, again, initially it appeared to be the more stable one, because it doesn't put a tert-butyl axial, you're still having more diaxial interactions here. Again, there are a few different ways to kind of think about this, but I think that this idea is going to come back on the homework, so just keep that in mind. Last thing I'm going to do, I'm going to pivot all the way back to practice 4, which is one of the ones from the practice handout that I skipped, mostly just because I really wanted to spend time on some of this discerning stereoisomers. So practice number 4 says, essentially there's this reaction that takes an acid chloride functional group and an alcohol functional group, and what it does is it plugs together this part of the molecule on the acid chloride and this part of the molecule on the alcohol. And the thing that's taken out of it is HCl. So we can do this with any combination. So let's do it with this acid chloride and this alcohol. So I'm going to abbreviate this whole benzene ring as pH, but it means the exact same thing. This stereocenter is going to be the exact same because we didn't react with it. We have our carbonyl, so all of this is from like the left side here. And then now I'm just going to take the O in this like pentagon and put it on. So we have the O, and then we have our cyclopentane. So predict the product. Cool. Now part A says only one of the carbons in the starting material is chiral. Or sorry, one of the starting molecules is chiral. Circle the one that's chiral, then assign its RS configuration. Well, the thing is, these both look like stereocenters, right? But in fact, only this one is chiral, in this stereocenter. And the reason is because here, this side going around the ring is identical to this side going around the ring. And so because of that, these are not two different things. This carbon is not attached to 4 different things. 2 of the things are going to be the same. So this one is achiral. This one's chiral. And then it says to assign the RS configuration. Well, okay, first is going to be oxygen. Then we have carbon, carbon, carbon. And so we list out. So we have here OOC. We have FFF. And then here we have CCC. So the second place winner is going to be the one with the Cl over here. And I think that L didn't get included. So this one, carbon is attached to OO and Cl. So priority 2 is going to be over here. Then the fluorine's priority 3, then priority 4. So what mode are we in? Ugh, annoying. We are in the plane mode. They gotta quit doing this to us. So we have 4 over here, 2 over here, 3 over here, 1 over here. I'm going to do my redrawing strategy. I hold it by 2, and then I rotate this one back over here, and then up and around. And when I do that, 2 stays in the same exact spot. I've rotated 4 to the dash, 1 goes forward to the wedge, 3 goes up here. Now we are in normal mode, and then I trace 1 to 2 to 3. It's counterclockwise, which is S. So this is the S stereocenter. Okay. Then part B, it says draw both of the expected products. So we draw the first one. The other one is the HCl that came off. And we did that first because that's the easiest. Then lastly, they found out that they prepared the wrong stereoisomer. So they wanted to prepare the S enantiomer, right? And we start off with the S stereocenter. But, apparently this is R. Like, let's verify that this is actually R now. So we said priority 1 is over here. And now let's look at the carbon. So this one we said was CCC. This one's FFF. This one changes a little. Over here, it was OOCl. But over here, it's OOO. So now without the Cl, who wins of these substituents? Well, Cl was bigger than everything before. But now the biggest thing that we have is fluorine. So in fact, our number 2 priority is here. 3 is going to be over here, and 4 is over here. Ooh. So what we've done is we've swapped the priority of things. And so I can like do this whole like redraw this and rotate and everything. But what it's going to show is because we've swapped priorities 2 and 3 here, this is going to now be in the product the R stereo center. So what happened? Specifically, the question wants to know, how can the student correct the mistake and get the S enantiomer from the reaction? Well, the big thing here is this reaction, because it's going to reclassify this acid chloride as now an ester, OOO instead of OOCl, that means that this stereo center, even though we don't react as it, it gets changed from being an S stereo center to an R stereo center because the priorities have been swapped. So if we know that this reaction is going to swap the stereo center from S to R, for example, then if we want to wind up with the S product, what we have to do is we have to start with the R enantiomer. So if we start with the R version over here, we know the reaction is going to flip it and it's going to become S as our product. And so that's how we get what we want. But very, very long video for all this. Hopefully going through some of it was helpful, but have a good week. Goodbye.